Thank you for the introduction. And many thanks to the organizers for giving me the opportunity to present here. It's been a fantastic meeting so far. I'm very much looking forward for the rest of this week. So I know that I specifically asked to change the title from light imaging with polarization to coherent imaging with polarization. I'm not sure that's very telling still. Probably a more appropriate title would have simply been to go with... That worked a second ago. There's some delay, but we'll figure it out. So what I'm going to talk about is polarization imaging with optical coherence tomography. So what I would like to cover in the next hour is obviously speak about optical coherence tomography, or OCT, and how we use that to look at polarization properties of tissue. We'll talk in some detail about how to reconstruct the depth-resolved tissue birefringence. So you see here an example of an OCT cross-sectional image of a coronary artery in a human patient. And here an overlay of birefringence and its optic axis orientation on top of that. So we'll talk in some detail about, I would also like to cover some practical applications where we use polarization as a contrast mechanism. And we'll talk in some detail about Jones matrices. And I would like to challenge you kind of throughout this presentation to think of Jones matrices really kind of as the lowest dimensional transmission matrix. So it's the smallest matrix you can get, but it's no longer a scalar problem. And if time permits, I would also like to talk a little bit about the higher dimensional transmission matrix work that we've been doing. And also please ask questions throughout if there's anything that comes up. I just wanted to start briefly with introducing my background. I think it's interesting for the younger scientists to see possible career tracks. So I have my undergrad and a PhD from EPFL in Switzerland, and then joined the Bauman Center for Photomedicine in Boston for a postdoc for kind of 2 years. So choose your institution for a postdoc wisely. You may wind up staying there for longer than anticipated. My team's research interests are really in polarization-sensitive OCT and also increasingly some multimode fiber imaging. Maybe a brief word on the Bauman Center for Photomedicine. So that's a thematic center at Mass General Hospital in Boston. It's a group of 270 engineers, physicists, and medical doctors, and it's a very interdisciplinary environment with a strong push, obviously, to translational research. Within the Bauman Center, I'm also part of CBORD, the Center for Biomedical OCT Research and Translation. That's an NIH-funded technology, I also need to read this, National Biomedical Technology Research Center. The mission of CBORD is to enable breakthroughs in biology and medicine through advancement in OCT technology. So we often team up with external collaborators, biologists or medical doctors that pose a specific kind of technical challenge that we try to solve with technical development, so to help solve their medical problem. Yes, we use polarization as contrast mechanism. And so generally speaking, tissue with a fibrillar architecture often exhibits anisotropy or birefringence. So this can be a combination of intrinsic and foreign birefringence. But in general, just the light now that is polarized along or orthogonal to this fibrillar components kind of travels at a slightly different speed. And thereby now changes the polarization state of that light as it propagates through the tissue. And as we'll discuss with OCT now, we can kind of measure the round-trip effect of these polarization changes as a function of depth into the tissue. And by observing these changes, we can deduce now the presence of birefringent material. Collagen, muscle, nerves are all fibrillar material that is birefringent and exhibits this contrast mechanism. We furthermore also have these multiple scattering effects or anisotropic scattering effects that generally just lead to randomization of the polarization states that can also give contrast on their own and enhance kind of our images. What I think is really fascinating about this is how these polarization effects basically provide insight into the tissue microstructure beyond the nominal OCT resolution through this kind of microscopic effects that define the polarization states. Now, is this finally working? All right. So, optical coherence tomography, Matthias mentioned it briefly on yesterday. It's just celebrated its 30th birthday a while ago. Many of you probably already have had an OCT scan of your retina. That's really the main application of OCT. It's now used routinely in ophthalmology or even by optometrists. In our development center, we focus more on endoscopic and fiber-based uses of OCT. And so here is a simple schematic kind of a typical OCT system. So we use a swept source, a wavelength swept laser source. And okay, one thing, a simple way to think of OCT is kind of as the optical analog of ultrasound imaging. But because light travels much faster than sound, we need interferometry to measure the propagation time kind of. And so we use, that was the wrong button. We use interference. We take a reference arm that we delay and interfere now with light that is scattered by the sample that we detect on our receiver, where we now record the signal as a function of the wavelength or the wave number. And then, in short, we take a Fourier transform basically of that interference fringe, and that's going to give us now the reflectivity profile as a function of depth into the tissue. So here's an example cross-sectional image of skin in the forearm. And so OCT then, in the lateral direction, it's a scan technique. So we use a loosely focused beam to illuminate the sample that we now scan by various mechanisms over the sample. And at each position now we retrieve kind of this reflection profile. And because we do interferometry, we really kind of sample the electromagnetic field that is backscattered by the sample. Now, another way to think about this, and I'm quite sure there must be some similar explanation for ultrasound imaging, is the object that we're really looking at is actually the sample susceptibility relating directly to the refractive index. So any change in that refractive index obviously scatters or reflects light. Now, if we take just the 3D Fourier transform, as it goes to reciprocal space kind of the sample object, because we scan in the lateral direction, the imaging system is a low-pass filter in that direction, kind of. So if you picture now, this is kind of the lateral and the axial spatial frequencies. So our filter kind of the imaging system in the lateral direction is a low-pass filter. But in the axial direction, because we image in reflection configuration, we sample these high spatial frequencies here. And what's really kind of intriguing about OCT is now each wavelength itself basically samples a specific slice here in this K-space, and all wavelengths together now probe kind of this K-space here. And by taking the Fourier transform now from K to path length, we really recover kind of that reflectivity profile. So in the axial spatial frequencies, OCT is really kind of like a bandpass operation, and in short, it's kind of a hand-waving argument how we get why we have speckle in OCT imaging. So if we look at this again more in the spatial coordinates, we can picture, similar to the ultrasound arguments yesterday, the sample is consisting of kind of point-like scatterers that are distributed through space, and each scatterer now contributes a small phase that depends on its exact axial position and the wave number, and thereby in the wave number kind of encodes its axial position. Now, we only measure this within the spectrum of our source, and hence, if we now take the Fourier transform of this recorded signal, we get the location of the scatterers convolved with this point spread function that, however, has a axially very steep phase slope, which again leads now to random phases on the individual scatterers, giving rise to these speckle statistics. So here we have mostly fully developed speckle, modulated kind of by the tissue structure. OCT nowadays is a pretty mature technology, so you get fast imaging speeds with like the A-line rate, so the sweep rate of a one wavelength sweep is in the 100 kilohertz range easily. You can get hundreds of frames per second. And the systems that I'm showing you today all have kind of a resolution of about 10 micron in the axial, 20 to 30 in the lateral. So the OCT community will pride themselves as this being high resolution compared to ultrasound imaging. Obviously, if you compare it to microscopy, it's not very impressive. The images, again, that I'm showing today mostly have been acquired kind of in this wavelength range here. And the imaging depth in tissue is kind of limited in the end by the transport mean-free path, roughly. So obviously depends a little bit on the tissue, but relatively shallow to 1 to 2 millimeters. If you do your system well, you get excellent sensitivity. You can kind of reach the shot noise and really get excellent sensitivity kind of to small changes in refractive index. And one of the unique opportunities now of OCT is because it kind of decouples, so it doesn't need a high NA to get axial sectioning. It gets the axial sectioning through the wavelength scan. And this has enabled relatively compact imaging probes, because again, we don't need optics that have high NA. We can use a loosely focused beam. And you can prepare these kind of neat probes here that you essentially take a single mode fiber and you can splice a coreless fiber to it. You fuse up a ball at the end that you angle polish to now have a beam that shines out to the side. You pack that into a drive shaft and inside a transparent sheath. And now if you rotate that probe and pull it back, you can kind of define a helical scan pattern surrounding that sheath, which is a convenient imaging geometry for many tubular organs. So this is commercially used for intravascular imaging of the coronary arteries and in a range of other applications. And it's really, so we do a lot of endoscopy. This really is intriguing for reaching kind of remote organs in the human body. So here's an example. That's a pullback now in a coronary artery of a human patient. You can appreciate here, you see here the sheath material of the catheter. Out here, this is a guide wire that is used to actually deploy this probe into the artery. It's metal, so it casts a shadow. And then here you see the lumen of the vessel. So the image acquisition is synchronized with the injection of radiopaque contrast agent, which is optically transparent and displaces the blood. Blood is not very convenient to image through, and that's how we can appreciate now the valve structure here in this coronary artery. We will return later to this, to kind of more the medical side of it. So now, because we do record interference, I like to think or say that any OCT system is sensitive to polarization, right? If we have interference, only the part of the sample light that has matching polarization to your reference arm actually contributes to that interference signal. And remember that in many of these systems, so we have a lot of fiber, and especially in this catheter case, maybe one detail to mention, so the catheter is rotating. So at one point in the system, you have what's called a rotary joint, where you couple the light from the static fiber into that rotating fiber. So polarization states are kind of continuously changing. And that's why a lot of even regular catheter-based OCT systems use polarization diverse detection, where we now take the sample light and split it into two orthogonal polarization states that we each mix with the reference signal to now record basically the field here, both along a horizontal and a vertical polarization state. And this way now, so this makes sure that we don't miss any sample light, because the light is going to interfere with one of the two the reference arms. But we can really think of this now as kind of the Jones vector. I mean, this is the classic definition of the Jones vector. And this Jones vector that we record here now basically describes our input polarization state transmitted now through the round trip transmission from the source to the sample back to the detector. And after we reconstruct our sample, under certain assumptions at least, we can now think of this path length resolved kind of polarization state as the effect of round trip transmission to a given depth in the sample. Brief side comment, so that the amount of birefringence that we encounter in biological tissues is kind of small. As we obviously know, birefringence results in different pointing vectors at one point, but the amount of birefringence that we encounter here is so small that we are just ignoring that effect. Now, if I want to really characterize the full Jones matrix, it's obvious that with a single measurement, I don't get the full information. And so generally, we need kind of a combination of multiple input states to back out the full matrix. There's various hardware ways to go about this. A convenient way is simply put the polarization modulator somewhere in the sample arm, where we now can sequentially kind of modulate the input state to get additional information. So there's some, more details on that, but in general, that's the concept of PSOCT. So again, PSOCT has been demonstrated kind of since the earliest days of OCT and has been used throughout for various applications. Now, since we're going to talk a little more about polarization and Jones matrices, and I'm sure you've all seen Poincare spheres and polarization sets before, but it's just, again, to make sure we're all on the same page. And since this is kind of the defining difference now compared to the scalar pressure waves of ultrasound imaging, here we have a transverse wave, and hence this polarization states. And so because it's somewhat challenging to visualize a two-component complex valued vector, it's kind of more convenient to transform this Jones vector into its corresponding Stokes vector, which we can conveniently plot out on this three-dimensional Poincare sphere. Right, and so if we have here this vertical polarization, that generally corresponds to a Q polarization state. And likewise, if we now have a horizontal polarization state, so it's obviously a little confusing in space now, or in spatial coordinates, we basically do a 90-degree shift of this linear polarization. On Poincare sphere, this corresponds to a 180-degree shift. We now have minus Q. And then obviously if you have linear combinations of these two base states, we get a linear polarization along U, or if there's an additional phase delay defining circular polarization, we are now in the V direction. Now, this is just the polarization state itself. What now if this wave travels through a birefringent medium? So now the input state goes through this medium that has a defined optic axis, so light along that axis travels at a slightly different speed than orthogonal to it. And this now continuously changes this polarization state, and the polarization state will kind of trace out an arc circle here on the Poincare sphere. If we change that medium optic axis orientation, we get an arc circle around a different direction, and here already we see intuitively how the effect of the sample is kind of to define a rotation of those polarization states on the Poincare sphere. And really to characterize the medium, if I have the same medium but launch a different polarization state, I obviously get a different evolution. But again, it's the same rotation vector here that was kind of changing these polarization states. So that, in a hand-waving sense, is again why we need two polarization states. So in short, we're trying to kind of find a 3D rotation of these polarization states. And in order to define a 3D rotation, rigid body rotation, if you know 2 points, that rotation is fully defined. One just brief sign comment on conventions in this polarization. So in my opinion, it's kind of almost impossible to get it right. There's various conflicting conventions on what's now left or right-hand side polarized light. It depends on first how you write your wave equation. Is it kx minus omega t or the other way around? And furthermore, yeah, do you look against the source or with the source? So you have, in my opinion, you have about a 50-50 chance to get it to match with someone else. Okay, so now quickly back to kind of this link between Jones formalism and Stokes vectors or Miller-Jones formalism. So again, we can here also more completely define this four-component Stokes vector, and here establish a formal link kind of using the optics-based Pauli matrix definition to define these Stokes vectors. And a brief comment here. So yes, the Miller-Jones formalism is kind of directly reversible to the Jones matrix. So there's an overall phase term that you kind of lose, but otherwise they define the exact same polarization states. However, again, because we have a lot of speckle, we generously average our signals. And if you now spatially average a Stokes vector, so the Stokes vector being incoherent, you now end up with a vector that in general can be depolarized. Okay, quickly going back to the Miller-Jones, Stokes vector in the Miller-Jones formalism, the I component is obviously equal to the Euclidean norm of the QUV component. But if you now spatially average these components, that's no longer the case, and you can get a degree of polarization that is generally smaller than 1. I'm not going to talk about at length about this, just to briefly illustrate this. So some while ago we really explored this as an individual standalone contrast mechanism. So these are tomograms of two glass capillaries, one filled with intralipid and the other with a suspension of gold nanorods. Gold nanorods, through their geometry, kind of are strongly have a strong polarization dependence in the scattering cross section. And if they're in suspension, they're kind of randomly oriented. If you now look at the polarization states of an individual point kind of in these images, you see that the gold nanorods are kind of all over the place, whereas the intralipid has a reasonably defined polarization state. And if you now spatially average these polarization states, you see how the intralipid kind of still defines a kind of fully polarized polarization state, but the signal of these gold nanorods kind of collapses into the center of this normalized Poincare sphere because it's depolarizing. And so this can provide kind of exquisite contrast to these gold nanorods at very low concentrations. Okay, now quickly going back again to our formalism here. In general, any 2x2 complex valid matrix is a suitable Jones matrix. Again, if you then construct the corresponding Miller matrix, you already can appreciate here that the 16 parameters kind of the Miller matrix have to be somehow constrained to define a Miller matrix. And then if you now go to the averaged Miller matrix or the general Miller matrix, you have a whole bunch of additional parameters that define depolarization. And I know some people here in the audience work on this topic kind of. There's a whole body of literature discussing kind of the exact physics and physical realizability of Miller matrices. But again, for today, we're going to stay more just on the retardance element or effect. A brief comment here on the dimensions. Again, I alluded to the Jones matrix kind of being the smallest possible matrix. It's very convenient to visualize these polarization states on the Poincare sphere, but I think this specific mechanism is not really amenable to scaling to larger dimensions because the dimension of the kind of equivalent Stokes vector becomes exceedingly large if your dimension increases. Okay, so a little more on Jones matrices, just to get a clear understanding. So again, what the Jones matrix especially, or a retarding Jones matrix here defines is two polarization states that are orthogonal to each other, and that one has a positive and the other kind of a negative delay. So they have a relative retardance in the case of a layer of thickness L and birefringence delta n of k delta n times L. The Miller, it can be overall scaled with a complex parameter that's kind of irrelevant. Now, okay, so that's kind of the intuition. Now there's a more convenient way to kind of really define the general Jones matrix, essentially through the exponential map of the special unitary group of dimension 2, where we can define this retardance vector, again kind of in the Stokes parameters, that now multiplies with each of these Pauli matrices. And again, just picture this as the 3D rotation axis in the Poincare sphere. And the length of the vector corresponds to the amount of rotation or retardance in that space. This can be extended to also include dye attenuation in a more general case. So far, we haven't really encountered any meaningful really dye attenuation in the samples we have investigated. So that's, again, for now, kind of let's stay in this, using this isomorphism between SU2 and the SO3 to kind of think of these polarization effects that we're observing. All right, so now on to how do we recover now the sample information. So again, if we think of the overall signal that we record consists of a sequential transmission of the light through system components, then the round trip through the sample, and then potentially some more system components. And again, we record this kind of in wave number space. And then as you remember to reconstruct these tomograms, kind of we independently take the Fourier transform of each matrix component. And now if you do Fourier transforms, I'm sure you remember multiplications result in convolutions, but in this case now these are matrices with convolve with each other, and this really can kind of mess things up if your system components here are now wavelength dependent. In other words, if you launch a certain polarization state of light for all wavelengths transmitted through the system, what arrives on the sample may no longer be a uniform polarization state, but have a polarization or a wavelength dependent polarization state, and that really can mess this up. In optical communications, that's kind of what's referred to as polarization mode dispersion or differential group delay. And so okay, I don't want to go into details. We had to come up with strategies to really compensate for these effects because they're present in especially our fiber-based imaging systems. And one simple way to think about it is you can take your spectrum and kind of chop it up into smaller parts, where each part is now less sensitive to this effect, do the processing there, and then recombine the signal after doing the processing for each bin. Now, what I wanted to spend some more time about is to talk about the fact that we measure round-trip transmission matrices, which imposes an intrinsic symmetry, and I think that's important, or that's along the point of Arthur this morning. This has important ramifications kind of for our signal. So what you can convince yourself is that the backward transmission from a given depth corresponds to the forward transmission to that depth transpose. That's only the case if you follow the convention of not flipping your coordinate system. So I understand that in antenna theory or some other places, there's other conventions where it's preferable to flip the coordinate system, but in that case, you don't see this obvious transpose symmetry. But if we now use this convention, you can easily convince yourself that your sample round-trip matrix that consists of the forward transmission followed by the backward transmission overall is now transpose symmetric. So this kind of eliminates some degree of freedom, basically, of your system. And if you now remember the definition of the Jones matrix, if you have a transpose symmetric Jones matrix, it means that it defines a linear retarder. So that the rotation axis that we talked about has to be in the horizontal plane of the Poincare sphere. In other words, we can't measure circular retardance or optical activity. It doesn't mean it doesn't exist, but in our round-trip signal, it doesn't have any impact. I'll get back to this again later. Now, that same symmetry obviously still persists also in Müller. Yeah, you have to just carefully explore the same formalism to find that same symmetry. Just briefly want to elaborate on, so this is not limited to a single scattering regime, but also applies to multiply scattered light. We'd like to kind of think that we mostly look at more singly or ballistic light, but obviously part of the light is multiply scattered. But if you picture now, so again, in a single scattering regime, it's kind of intuitive that you would get that transpose symmetry. But if you have a multiply scattered path, you can think now of a sequential polarization effect here taking place, which on itself doesn't observe the symmetry. But now back, our imaging geometry is we use basically the same single mode fiber to illuminate and detect light, right? So we are in a perfect backscattering direction. Our S&P scattering planes are not defined because we were normal to the sample, basically. So that, which means that at the same time, kind of as if you detect a photon going from one side to the other, we also have the counterpropagating photon, which now reestablishes that the overall observed signal has to have this transpose symmetry. So this is kind of related to, I think, the weak localization of light or enhanced backscattering. Okay, so now we established that the only effect kind of that we can observe is this linear retardance. Now, the last point I want to go in detail about is that how we get now the depth resolved tissue signal. Because so what we measure is what we call the cumulative round-trip retardance. So again, and that's mapped out here. So you see here that the round-trip retardance through this tissue wall, which is really difficult to interpret. What we want to get at is kind of, we want to look at the small segment here, a small incremental depth delta z. And if you picture now, so at one given depth, again, we have this round-trip signal. And at the increased incremental depth, we now have, in addition to this forward matrix, a small round-trip matrix through that thin tissue layer, okay? And if we now want to, if we simply take now the inverse matrix product of these two terms, we can isolate, or we obtain a similarity transform of this round-trip matrix. Similarity transforms preserve eigenvalues, which define the amount of retardance. So by taking this kind of inverse product, we can actually back out the amount of scalar retardance that we observe across this thin tissue layer here. And we can convert this, it's not indicated here on the scale bar, but we can kind of get a quantitative measure of the refractive, of the tissue birefringence that we observe. And in this case now, you can appreciate an increased birefringence here in the medial layer, which is rich in smooth muscle cells, and here in areas with increased collagen content and potentially some cholesterol crystal here in this lipid ridge area. So, and just want to give you another look or another way to think about this. Think again that the round-trip Jones vector that we observe, the detector that corresponds to the round-trip transmission. What we want to look at is kind of the depth dependence or the path length variation of this polarization state. Now, this corresponds to the derivative of the matrix. This is independent of depth, but can be expressed as the inverse product of J with T. So you can now relate the variation of the polarization state to itself times this differential matrix. And that differential matrix, if you now discretize that, you find that's exactly kind of the expression we're looking at here. So in other words, what we're kind of looking at is the depth derivative of our round-trip Jones matrix. But what we really would like to get at is this round-trip thin layer matrix here, right? So if we knew the forward Jones matrix to that depth, we could simply correct our measurement with that to isolate this round-trip matrix without that similarity transform. This way, we could also get the eigenvectors, which now define the optic axis orientation of our local tissue layer. So this is now back to the intrinsic problem of this round-trip symmetry. How can we find kind of the forward transmission matrix from round-trip measurements? Because this forward transmission matrix can be channel retarded. It's not constrained. It's a sequence of multiple layers that can be differently oriented, so it can define a channel retarder. So the only approach we can take kind of is iterate from the tissue surface and build up our forward Jones matrix as kind of the stacked effects where we measure each thin layer. And here we have to take the assumption that that thin layer is indeed a homogeneous linear retarder, which I think for many tissues is a safe assumption, but still there's some clear assumptions in there. But if you now do this, we can now back out, in addition to the birefringence, the optic axis orientation. So we have now in color here the physical optic axis orientation, and in brightness the amount of birefringence. And you can now appreciate here how that muscle layer in that tissue layer has a circumferential orientation in the blood in the vessel, and the collagen here a more longitudinal orientation. And again, just in the view of that we took before, this is now the actual depth derivative of our forward transmission matrix, or forward Schoen's matrix. So again, what we did here, I think, is somewhat similar to a multi-slice assumption, kind of, where each layer we treat kind of as consisting of maybe point-like scatterers, but being in a background medium that has a defined birefringence. And we now kind of layer by layer, or kind of onion peeling back out what are the optical or birefringence properties of each layer. All right, now just briefly, you may have realized how I masked out certain areas in these images. So that's where we now still use kind of this degree of polarization, which first and foremost here acts kind of as a reliability metric. Areas that are kind of in the noise have no more information, and we kind of use a DOP threshold kind of to mask out those areas. You still get actually in the coronary arteries, there's some intrinsic contrast to depolarization that highlights lipid particles. But I'm going to get back again to this issue with the round trip matrices, because so far I didn't explain yet how we deal with the fact that we now actually image through a rotating catheter. So the catheter is part of the round trip symmetric part of the system. But if you really want to isolate here, or what we so far described as the sample matrix, consists of the transmission through the catheter, followed by the tissue forward transmission and the reverse transmission. And now, because it's a fiber that is itself, the reflection in the ball lens acts as a linear retarder. So it's basically a birefringent element that is changing as you rotate the catheter. So we need to clearly back out this effect. But again, if you now simply look at the signal from the sample surface, all we observe is a round trip linear retarder. So here I'm going to briefly allude to kind of this, what's called apparently the bipolar decomposition, that says that any including complex valued matrix, can be decomposed into a sequence of a transpose symmetric. And again, I'm going to highlight, so this is a regular transpose operator, not the dagger, not the complex transpose, into a transpose symmetric part and an orthogonal part. So an orthogonal matrix, then the transpose is its inverse. If your matrix happens to be unitary, it means that it would be a real valued unitary matrix, this V term. But now you can easily appreciate here, if you plug in this LV decomposition here, you see how the V term cancels out, and the only part you can recover is this linear retarder. And with that linear retarder itself, you can cancel that linear retarder, but you remain, the signal you recover is a similarity transform of that V matrix. Now again, in Schoen's, this V matrix is a rotation along the V coordinate, which now simply results in a rotation of the optic axis that we observed for our sample, which is confined to the QU plane. So in order to get really interpretable optic axis orientations, we now need to figure out still this V term, which we can do by either modeling the catheter rotation, or better by using residual birefringence in the sheath as a guide star, kind of to compensate that transmission through the catheter. Now, if you go through all that trouble, we then get these maps here now of, in this case, coronary arteries, where we can appreciate these various tissue layers with different physical orientations and different expressions of birefringence. At the time, at the reviewer's request, we had to build a phantom with a two-layer phantom here that we could independently change the orientations to now show how this really is critical kind of to back out the correct optic axis orientations. Okay, the images are kind of difficult to look at, but if you focus over here, if we don't do this layer by layer correction, if you kind of ignore the effects of the preceding tissue layers, you still get a correct measurement for your first layer. Okay, we corrected for the catheter here, but not for the depth in the tissue. but the second layer will be totally off depending on the property of the first layer. So you really need to go this layer by layer approach to get a correct kind of estimation of the optic axis orientation. Okay, so now I want to quickly step away from just the Jones matrix to kind of the transmission matrix of a multimode fiber where, well, I'm a little dismayed how much trouble we have to kind of manage that round trip to forward transmission algebra in case of the Jones matrix. But that exact same symmetry or algebra kind of applies also to a multimode fiber. And yes, so deducing the forward transmission matrix from a round trip measurement is, I find, a big challenge. So some time ago, we measured the round trip transmission matrix through a piece of multimode fiber simply by scanning. So this is the point basis kind of transmission matrix. We scan a spot over the multimode fiber. In this case, we measured this for a single polarization state, and we explicitly used a mirror at the end to direct the light back, and then detected on the camera with off-axis holography our transmission matrix. So we then took each of these images, kind of linearized them up to build kind of our transmission matrix here. And now, our goal was to convince ourselves that this transpose symmetry indeed is present. And so if you now take the measured matrix and compute its transpose inverse, if it is transpose symmetric, it should cancel out and give us basically an identity matrix. On first attempt, obviously, this doesn't work out because there's slight inaccuracies in the system between the illumination and the detection part, but those are optical aberrations that can be easily estimated, and then we indeed found or can confirm that likewise in this larger dimensional transmission matrix, we observed this clear transpose symmetry. All right. Now I want to briefly switch kind of topics or to tell you about some applications kind of this polarization, so back to polarization sensitive OCT. So the first application, as you've already seen, where we kind of really performing clinical studies currently, is to look at the coronary artery disease, which remains kind of one of the main killers, if you want, in the developed world. So the preferred way to treat someone who suffers a heart attack is with percutaneous coronary intervention, where you put the catheter into the coronary artery to kind of perform advanced plumbing, if you want. You remove the blockage and probably implant a stent. Intravascular OCT is increasingly used to guide these procedures, and has also become an invaluable research tool really to study the pathophysiology. Like unlike other diseases, you can't biopsy the coronary artery in a living patient for obvious reasons. So the only way to gain insight is really by doing in vivo imaging. And there's this conundrum that a lot of patients who undergo a PCI procedure, or 1 in 5 patients within a few years usually returns with another event. And so the idea is if we could prospectively identify lesions that are likely to cause events in the future, you could do something about that during this first visit. And that's where we thought that maybe with polarization we could make a contribution. So very briefly, here coronary atherosclerosis consists in the buildup of lipid material in the vessel wall. If this lipid material is kind of separated from the bloodstream here by a thin fibrous cap, that is and collagen there is the main extracellular matrix protein that provides stability. If there's not enough stability or not enough collagen, that cap may rupture, release this material into the blood, where it will thrombose and cause a blockage of the blood vessel. So that's the most fatal complication that can lead to a myocardial infarction. In other cases, these lesions kind of heal up and become more scarred, really collagen-rich tissue, where they simply block the blood flow, but you're no longer at the risk of kind of dying from it because of an acute event where it ruptures. The main tool in the cath lab to guide these procedures is angiography. So that's X-ray kind of through the patient. You inject now, this is back to this radiopaque contrast agent that is injected into the blood vessel to get contrast in X-ray. And if you look very carefully here, you see the small dot pulling back. That's the radiopaque tip on the OCT catheter that is performing here a pullback. Again, while that contrast agent is in the vessel, the blood is displaced, and you get actually a view on the artery wall. Because this is compatible essentially with commercial catheters, this facilitated kind of the translation. So we built a custom OCT console here, but interfaced it with commercial catheters, which allowed us to relatively easily perform studies in human patients. And I want to slowly speed up a little bit. What's intriguing here now is that some of these features, if you look at this vessel wall kind of in these two patients, have a very similar intensity image in OCT, but a very different birefringence, which suggests now that the material of this tissue here may have a very different composition, which could have implications for the medical therapy of these patients. We did a bunch of kind of preliminary pilot studies where we compared, for instance, acute patients, or where we compared the birefringence inside the fibrous cap now of these lesions between patients that suffered an acute event or a plaque rupture and patients that have that more stable phenotype, so where there's no lipid pool really, where patients simply have a blocked vessel due to collagen. And kind of matching with that hypothesis, the stable patients have a higher birefringence in their caps than acute patients. Likewise, we looked at kind of fresh thrombi that are healing up in the vessel wall, and there we also found that thrombi that are older and have already more collagen because they undergo wound healing have a higher birefringence than more acute thrombus, which again could have implications into how to medicate these patients. So this work really has been spearheaded by Kenichiro Otsuka, who at the time was in our group, is an interventional cardiologist, and we now have several kind of plans, at least, for further studies with a clear clinical hypothesis. From a technical point of view, the challenge right now is that this is a custom PS system, and it's kind of difficult to get this multiplied. So one recent effort that we have been looking at, so I explained how normally we need to now modulate this polarization state in order to be able to take these PS measurements. Interestingly, some commercial instruments have polarization diverse detection, again, to avoid the polarization fading artifacts that you may run into. And so this offered the opportunity for us to kind of basically using now to our benefit the fact that the transmitted polarization state often depends on the wave number. We came up with a way to kind of encode that spectral dependence, or encode our illumination polarization state, encode a spectral dependence on our input polarization state. So instead of actively modulating the polarization state, use that intrinsic variation. That, again, that only works by recognizing the intrinsic symmetry that is present in these Jones matrices, which then allowed Georgia in my team here to come up with a reconstruction method that allows now basically to get the same amount of information using a single input state as we previously got with this actively modulated dual input state system. Okay, now another application that we're currently looking at is to use PSOCT to help guide stereotactic neurosurgery. This is a collaboration effort with the Cerveau in Quebec, and the rationale is that myelinated axons are known to be birefringent, and you've seen that the form factor of our probe really is kind of amenable to imaging in a stereotactic setting. So I'll explain in a second. So the main application here is to look at deep brain stimulation surgeries. So deep brain stimulation, very along the line of the talk this morning, but not with optogenetics, but more brute force, an actual electrode that is implanted deep into the brain is a very efficient therapy for motion disorders, mostly due to Parkinson's, where you can really suppress the tremor that comes with this disease. And so it consists in implanting this electrode deep into the subthalamic nucleus. This is done again stereotactically, so you attach a frame to the skull, do pre-surgical planning, and then kind of bring that probe to the target location within the brain. Obviously, this procedure has certain errors, and the efficacy of this therapy really relies on utmost precision. Again, our OCT probe basically matches very closely existing stereotactic neurosurgical tools, and we think it should be straightforward to kind of integrate this into the setting. So this is preliminary work. We just imaged here this is porcine brain ex vivo, first in a benchtop configuration. So this is a wide field image of this coronal section here, where even in the scattering signal you can appreciate different white matter tracts that are oriented different directions. If you now look at the optic axis orientation and birefringence, well, on the screen at least, you get better contrast. You now can better appreciate the orientations of these white matter tracts and also the presence of these individual fiber bundles. And yeah, we can do this with the catheter, where again now we can, even within depth, so this is longitudinal cross-section through this catheter view, where you now can appreciate these individual bundles kind of at various position in depth. And in the longer term, so the idea is then obviously to put this probe now deep into the brain, where you can get then this full view here, where you can highlight individual tracts. So where we're going with this, or where we plan to go with this, is to really rely on this close analogy of PSOCT, or the optical anisotropy that we image with polarization contrast, to the diffusion anisotropy that is used in diffusion tensor imaging with MRI. Sure, you heard of that, where if you do MRI on the different gradients, you can back out the diffusion of these water molecules, which physically occur along these tracts. And so Hui Wang, a colleague, has done this work where she compared PSOCT images, so the birefringence and optic axis orientation, to kind of MRI-deduced contrast. And I think visually this gives a very convincing, makes a convincing point that this contrast intrinsically is very similar. And we trust that pre-surgical diffusion tensor imaging could serve as a template, where if we now insert a probe into the brain, we could locate or identify the exact location of that probe to confirm or identify the ideal location to implant these electrodes. Now, one more comment. So far, all the optic axis orientation that I refer to is obviously the apparent optic axis orientation in the azimuthal direction. But if we think that optic axis orientation may have a 3D orientation in space, and again, all that I'm observing basically is the effective birefringence, which kind of relates to almost the projection, but it is an additional sign term there, of the actual 3D-oriented optic axis orientation. And so a remaining challenge that we're currently addressing is that in order to back out the true 3D orientations, we basically now have to combine image measurements at multiple angles to back out the 3D orientation of that underlying optic axis orientation. So I think in the interest of time, I'm going to skip through explaining you the third application of birefringence in the posterior sclera of the eye, just very briefly. So this is kind of the more typical application of OCT, where you image the retina. This is the anterior retina, but here we really focused on the collagen of the sclera, so the white part of the eye, but at the back of the eye, which turned out to be an interesting biomarker for pathological progressions of myopia. But I would like to spend a few more minutes to just go over some work on the multimode fiber side. So I did explain how these probes really define a convenient strategy to define a very compact imaging probe that can reach remote organs. There's other more classical endoscopy approaches, but they are all pretty complicated engineered systems. Or we saw that the fiber bundle of this morning, that is an interesting solution, but still is a complicated, expensive instrument. And so we have been really fascinated by this notion of using a single multimode fiber kind of as a guide to act as a miniature endoscope. And so, I mean, this is, I've showed you before already a transmission matrix now of the multimode fiber. This is just, again, to illustrate how illuminating a spot on one side of the fiber results, obviously, kind of on a speckle field on the other side. But again, this is now kind of my high-dimensional Jones matrix. You can relate the input and the output field in this linear fashion. And if we now perform an image through such a multimode fiber, and I think this is very analogous to what Matthias was describing. So here we simply measure the round trip reflection matrix from the proximal side of the fiber. So we scan a point over the fiber, and the light goes through the fiber, illuminates a sample, comes back through the fiber, and we detect it on the proximal side again. And then it's all in the computer, and everything else can happen in the computer. And I can then take my round trip matrix and okay, the challenge here is I need to now know the transmission matrix of my fiber. If I do know it, I can now compensate for the transmission matrix through the fiber. I can compensate for propagation through free space to whatever sample depth I want, and can then recover basically a confocal image from a given sample depth, which we kind of did the first experimental demonstration here with the cover slip. This is kind of the integrated signal where you can clearly identify the two signals, and we could just make out kind of the two cells that were stuck to the front and back face of that cover slip. Okay, very last slide. Where we would love to get to, or where we did the very first stab, is kind of to now combine these two approaches, so do coherent skating through a multimode fiber. So this is even more daunting. We still don't know how to get the forward transmission matrix from the round trip matrix. To do this, we need to know the transmission matrix now at multiple wavelengths. But if you could do that, you could then do coherent skating through the multimode fiber, and this is a very preliminary result here, where we placed a cover slip in front of the fiber, and all we can make out right now is the reflection from the fiber facet and then the front and back interface of this cover slip. This is the confocal image, because as you go away from the fiber, your NA decreases. You have very poor optical sectioning, but with coherent skating, you can clearly make out these interfaces. All right, so just to very briefly summarize, no, maybe I'll skip the explicit summary, and just want to highlight again here I think there's a lot of at least linear algebra that we could learn from working with Jones matrices, but a lot of those concepts, I believe, really do equally apply to multimode fiber endoscopy or imaging in general complex media, trying to compensate for scattering. I believe the main challenge is kind of to get that forward transmission matrix from the round trip matrices or from the round trip measurements that we have available. And I would like to thank my colleagues and collaborators, and thank you for your attention.